Hello, I am Adnan, and this is a retrieval augmented generation or a RAG-based chatbot application that I have built over Core 3GPP 5G specifications. The problem it solves is simple to state and harder to solve. These specs are hundreds of pages dense. To be precise, each file uh, consists of somewhere between 500 to 700 pages of data. And in total, we have got seven files. So we are dealing with huge amount of data itself. So while building this application, our major goal was to build an application which can generate output or give response with as less hallucination as possible. So this application is built by keeping that goal in our mind. So let's move forward to our tech stack. On the tech stack side, we have used a fast API backend and a Streamlit frontend, and every model's call is routed through a single light LLM gateway. The Gamma 3 4 billion model is responsible for the generation and checking the groundness of the response that gets generated. Then there is Llama 3.21 billion, which acts as our query analyzer, and the images are getting processed by using Lava model. All these models are served locally through Olama, so no spec content or user query ever leaves the machine. The retrieval is a combination of semantic search and a BM25 keyword search. So it's a hybrid searching technique. And on top of that, we're using a BAI embedding model and a encoding re-ranker, cross encoder re-ranker as well. And our vector data is stored in Chroma Vector Store as well. Then we are implementing Redis as a cache memory to handle the session memory, and Logfire and Langsmith is used for traceability and gives us full observability into every call. Now, these are some tech stacks which I have implemented or tried to implement in this project. Now let us talk about the architecture itself. So architecturally, there are three stages. First is the ingestion. So the raw spec documents are parsed using their native heading structure. So clause boundaries stays accurate, and they are chunked with a contextual header on every chunk and embedded into the vector store tagged by their specific clause and modality. The second layer is our retrieval layer. An incoming query goes through a query analyzer. Then the hybrid search takes place, fused together, and re-ranked for precision. The third step is our generation step. This is where the hallucination prevention actually lives. A confidence gate checks the retrieval's quality before anything gets generated. If the quality is too low, the system refuses instead of guessing. Every answer that does gets generated is properly citationed, meaning every claim has to carry a specific and a clause tag. And a groundness check varies each citations against the retrieved text before the answer is ever shown. If that check fails, it regenerates or it retries once, and if it still fails, the answer goes out clearly flagged. So this is a official documentation. So the output which gets generated must be properly citationed. So that is why these steps are taken, which are necessary for the quality assurance and to make sure that the output that gets generated are as less hallucinated as possible. Now let's move forward to our LLM evaluation part. On evaluation, I ran two independent checks. An automated harness measured a 96% retrieval hit rate, a 100% correct refusal rate on out of corpus questions, and a Regis faithfulness score of roughly around 0.88 to 0.90, which is 88% to 90%, meaning the vast majority of generated claims trace directly back to the source spec text. I also manually scored the system against 20 chosen question spanning of a text lookups, tables, cross-document reasoning, and images and diagram interpretation, protocol stack figures, architecture diagrams, roaming scenarios. Out of those 20 questions, 13 of them came back with low to no hallucination at all.